Right, good morning everybody. My name is Alan Beech. I'm the Sales Director for Clarke Energy. And today I'm going to talk to you about addressing the net zero trilemma. If you're not familiar with that term, it's maintaining sustainability or achieving sustainability whilst remaining affordable and keeping the system reliable. Just some insight into Clarke Energy. This is the sort of, are we big enough to cope and small enough to care? And our competition will have very much the same claim. So today what I really want to present is what's applicable to the technology rather than just us as Clarke Energy. So 8 gigawatts of installed capacity. We have a global footprint of 28 countries, from Alaska over to Australia and us in the middle. And we have local support as well. As you see there, we've got a large stock holding in the UK and over 100 engineers supporting the product to ensure maximum availability. Okay, just some insight into the overall message today. I call it reality check. What we see here is the 4 energy scenarios that the ESO publishes every year, and what we have there is the various renewable technology ambitions across the net zero from 2030 to 2050. And what you see there is the diamonds on those columns is that what they estimate to be the peak demand. And so you see that we've got at least a 2 to 3:1 ratio of renewable energy versus the actual electricity that they project us to be using. Now, on the right hand side there, you see the problem that we have on the electrical system, that majority of our renewable energy is up in the northwest of the United Kingdom, whereas the majority of the demand is in the southeast, etc. And that's causing a lot of sort of grid connection issues. Now, a lot of this excess wind should help us to meet our ambitions of achieving green hydrogen rather than curtailing. Curtailing is where we're switching off wind energy that we do today, and the bill for that, for balancing the system, is now in the billions of pounds. On top of that, there should be 5 gigawatt of blue hydrogen as well, which is the natural gas that's produced with carbon capture technology and stored in offshore oil wells. Now, this is probably the most important slide today for the sort of reality check, people who have CHPs and are on the path to net zero. What we see here is a typical very green day, showing you the UK generation stack of wind energy, solar, but even on the greenest days, in September we set a new record of an average of 27 grams per kilowatt hour for one 30-minute period. But we still had over 14% of our electricity generated by gas. So burning gas at our traditional centralised gas turbines, whilst efficient for producing electricity, all this advantage is lost through the transmission by the time it reaches its point of use, and there's no waste heat recovery like you have out of a CHP. Now, due to the existing and numerous constraints on our electrical system, we already have great difficulty in electrifying our economy, so there is a need to support the transition by not doing too much too soon. So, whilst we still use gas in our central gas turbines, your CHP's electrical content could actually be considered as net neutral, and the heat generated as a means for offsetting your carbon until other options such as hydrogen, etc., become commercially available. That should also help to alleviate the system constraints on the electrical system and provide resilience in the event of a whole grid failure. So here we see, with the onset of hydrogen that's planned to come through, we see that the national gas have committed to transmitting throughout the UK, and here we see the hydrogen backbone through the UK, which would be linking up the hydrogen clusters where they're producing blue hydrogen, and where electrolyzers will be able to inject the green hydrogen into the system. And on the right hand side we see the ESO's planned upgrading the grid using a supergrid offshore, which will link up all the offshore wind farms and bring those into the southeast of England. But both of these are facing a lot of public outcry, we'll call it NIMBYism, where they don't want the DC to AC transmission upgrade sites in Norfolk, etc., transmission centres around the country, and we've seen in the northwest of England a trial village that was supposed to be running on hydrogen due to public objections. That's been knocked back. So, hydrogen and your CHP fleet. Here we see the two types of grids that we'll be having in the UK. One will be the repurposed blended gases of natural gas and green biomethane, plus the natural gas, up to 20% hydrogen is planned, and then also the hydrogen backbone, which will be connecting all those grids that was mentioned earlier. And we have our generators today available to deal with both the blended and 100% hydrogen. So, hydrogen, will our assets become stranded? No, the technology is there now, and any existing systems can be upgraded at the appropriate time. Now I'll just expand a little on some of the issues. Technical slide here showing the effect of hydrogen blending on main gas. There's something in the industry we call the wobble index. There's the methane number and the heating values all get reduced as soon as we start injecting hydrogen into the system, and at 20% you're basically getting 15 to 20% reduction in the methane content of the gas. Now 20% injection doesn't give you a 20% reduction in CO2, and what we see here is the graph that says at 20% you're getting 7% decarbonisation, but it is a reduction, and blended with biomethane with carbon capture at source, which is technically a negative carbon gas, it is a reduction. Now, due to the higher flame temperature that's experienced with hydrogen, there is a risk of engine stresses due to knocking within the system and raised NOx emissions if not checked. So this is dealt with in a simple term by monitoring the hydrogen content coming down the pipe, so that we can control and adjust the NOx levels and reduce peak pressures to reduce that engine stress. And that is done on anything up to sort of 25% hydrogen once you go above a 5% blend. The technical differences between a hydrogen blended up to 25% and 100% hydrogen is basically within the fuel system itself. So we see on the left there the conventional system, where the gas and the air is mixed before the combustion system, and then on the right we have to inject the hydrogen straight into the cylinder area, sort of post-fuel injection. So with the transition and the path to net zero, we have three options available today, where the engine can take up to 5% and then 25% with minimal change to new units or existing units. Once you go above that 5%, we just need to monitor the hydrogen content so we can control those engine stresses and the NOx levels. And then we can go to the mid-level, that if people start blending more than the 20 to 25% that will be coming through the mains gas, we can have one that can take anything mixes and swap between 100% natural gas, 100% hydrogen, and any blend in between. And then finally we have the C1, that is optimised for 100% running on 100% hydrogen. Here we see the range and the aspirations of where we go with the range, and the most typical engine within the NHS fleet is our Type 4 Jenbacher engine, and as you see there, that's available today and has been available for 12 months to buy at 100% hydrogen and can be converted on existing fleets. And we should see the rest of the fleet up to the Type 6 during the course of next year for 2025 full release. Now today, on that 100% Type 4, we are seeing about a 30% reduction versus a typical mains gas-fed unit today. But based on past and current evolution, our R&D departments are confident that as long as 100% hydrogen becomes commercially available, not only can we attain the same levels that we get on mains gas today, so eliminating that 30% reduction, that we should be able to exceed those outputs as the pressures of hydrogen. We'll be able to get more hydrogen into the cylinder and the requisite number of air. Here we see an example of a project that we're just putting in commissioning at the moment for a data centre in the Netherlands, just to give you some confidence what can be done on a system that's running on both mains gas and hydrogen. These are standby units for a data centre that wants to be totally green, and they've got 1 hour storage on site of green hydrogen. And most events, say 99% of grid failure events, are less than 1 hour, so they see that doing the majority of their backup. But if the grid failure is beyond an hour, it can seamlessly swap over to 100% mains gas. Now, hydrogen is not the only game in town, and we have other complementary technologies. We have thermal electrical stores, which can reduce engine run hours, and if you reduce the run hours, the life expectancy of the equipment goes up proportionally. So typically they run 8,000 hours a year at the moment. As we see more green electricity coming onto the system, you may want to reduce that down to 6,000 or even 4,000 hours. But that means instead of a 15-year asset, brand new, it becomes a 30-year asset. We can also recover previously lost heat off some of the lower temperature systems and put that through a heat pump. It can support heat pumps directly through the electricity it produces, and also any vehicle charging systems. There's various carbon capture technologies, some of which have been supplied for many years for the greenhouse industries, for food growth, marijuana growth, legal marijuana that is. Food and drinks industries, Coca-Cola, we've got operations there in Northern Ireland and in the US, where it's food grade carbon dioxide that puts the fizz in the drinks. Last year you'll have heard about the crumpet crisis, when the fertiliser plants stopped producing because of energy prices, and the CO2 going into crumpet manufacturers caused a problem. And we're also doing a prototype with Severn Trent at the moment, which turns that carbon dioxide into precipitated calcium carbonate, which is a product that's used in paints, paper and drug manufacture, and is actually a saleable product. And we look to get that into commercialisation by the end of the year, by the end of the decade. And there are other technologies coming along as well. Obviously, if there's 100% hydrogen, there's no carbon to capture, so it's a bit of a two-horse race on that. Then finally we see sort of smart energy grids, which decide which energy source to use at any point in time. It uses site-based data and external data such as weather predictions, electricity prices, to ensure that the lowest carbon energy source is being provided at the time, or the lowest cost energy source, but typically they should be the same going forward. And it can even trade that electricity back to the grid if the system is under difficult constraints. Also another revenue stream. So, point of this is really there is no silver bullet. We need to use everything within our ability, but when it's ready and not killing something today, because at first glance it may not look good. So yes, it may increase your Scope 1 emission reporting without the carbon offset qualification of the heat, but really it's a cumulative effect we're dealing with in global warming. It's not a site-based issue, it's UK PLC, it's the CO2 emissions that we need to reduce. So CHP, with its resilience, with its payback of less than 2 years on a typical installation, and its actual carbon reducing capabilities when compared to central power stations, it really does meet the trilemma of sustainability, reliability, and the other one which I've just forgot. Thank you very much. Any questions, anyone? No? Successful presentation? Oh. The impact of the cost of hydrogen. $1 million question, but it won't be $1 million. It depends on what subsidy the government decide to give to it. They have said that they hope to provide hydrogen parity with mains gas. But that doesn't say what they're going to do to mains gas. To get, that could come from two ways. We do see in the US with the Inflation Reduction Act that there people are being subsidised. I think it's $3 per kilogram. So that brings the hydrogen price within reach. But it depends how often you're using your generator as well, because it makes sense to run on hydrogen or any fuel if we're in a time of the Dunkelflaute. If the wind isn't blowing and the sun isn't shining and we've got 80% reliance on renewable technology, well, if that's not there, the only source of electricity will be from our hydrogen stocks, which will be stored off-site. So the price of electricity will be sky high. So the cost of hydrogen will somewhat become academic. But really using it to produce energy is a very inefficient way of using hydrogen. It should be used first for those hard to decarbonise type areas that is used in industry, steel manufacture, heavy duty construction engines, agriculture, etc. Typically it takes just shy of 4 megawatts of electricity to produce enough hydrogen to produce 1 megawatt of electricity out of an engine or a fuel cell. So that doesn't really make sense until you look at the slide that showed the 3 to 4 to 1 ratio that we'll have. That is when we've got so much electricity, it makes producing hydrogen worthwhile. And we're putting in storage sites, Centrica, there they are expanding the rough caverns to take hydrogen, etc. So whether that becomes a strategic asset for those times, or whether it becomes a marketable wholesale gas, we just don't know. So, but one thing about CHP is it's the most efficient use of energy in to getting energy out if you're using full heat recovery of all the systems and running alongside heat pumps and everything else. So it should never be really taken out of your energy mix, is my point today. And that's not only of a vested interest of Clarke Energy, but that of a taxpayer, and I have grandkids as well, so true believer in net zero and the climate crisis. Yeah.